Hello, today we have lecture 20. We have already seen that del H mix equal to x A x B omega, and omega is n 0 z E A B minus E A A plus B B by 2. This is my omega. Now, when we consider ideal solution, this del H mix is 0, but if we consider non-ideal situation, that time del H mix can have value greater than 0 or it can have value less than 0. Now, we started working on the situation which is the first situation where delta H mix is 0. That time we saw that if the situation is like, if this is my minus TΔSmix and if this is my del H mix and x b, this is pure A, pure B, this is G. Now, del G mix is del H mix minus T del S mix, and here del H mix greater than 0, but if we compare this value as well as this value at all the concentration level from this concentration to this concentration, I could see del H mix is less than minus T del S mix, the mod of this value. So, that case del G mix would be all the time negative over the entire composition from 0% B to 100% B. So, my del G mix would have value between del H mix and minus T del S mix, and since this condition is valid for all the concentration from 0 to 100% B, then del G mix would also be negative. This would be my del G mix. So, situation is not changing much if we compare the situation where del H mix is 0. Had this been 0, only difference would have been this line would have been del G mix when del H mix is equal to 0. That means, only difference is the how steep is going to be the del G mix. If it is positive, then the stiffness of, that means the negativeness of del G mix would reduce. But situation would be little complicated if we have a situation when the graph nature is like this. This is my del H mix x b, but minus T del S mix if the condition is del H mix is greater than minus T del S mix, except x b tends to 0 and x a tends to 0. These two compositions, except these compositions, all other compositions, this condition is valid. So, if I try to see the minus T del S plot, from this picture it is seemingly observed that del H mix is all the time greater than minus T del S mix, the mod of that minus T del S mix value at all the concentration, for all the concentration x b equal to 0 to x b equal to 100, but the situation is not like that. Now, if I try to see the slope of this line at x a tends to 0 and here x b tends to 0, it would lead to some exciting situation. Now, we see that del G mix is equal to del H mix minus T del S mix, which can be written as x a x b plus R T x a ln x a plus x b ln x b. I can write it as 1 minus x b plus R T 1 minus x b. I just convert in every composition in terms of x b. Now, if I try to find out the slope of this del G mix plot, then with reference to x b, it would be 1 minus 2 x b plus R T plus it would become now when x b tends to 0, what happens to ln x b 1 minus x b term? Actually, if x b tends to 0, ln x b would be equal to minus infinity. Hence, d del G mix dx b would be minus infinity when x b tends to 0. Similarly, if I consider in this plot, we have considered the slope at this point on del G mix curve is minus infinity. Same way we can prove that tends to 0. So, this is the slope of del G mix on two extreme ends. Now, similarly, if I try to find out the slope of minus T del S mix x b when x b tends to 0, it would be also minus infinity. Therefore, it is very clear that the slope around this point and around this point for this particular line minus T del S mix is minus infinity. So, whatever could be the value of del H mix, that means the finite value of del H mix around this zone, this condition would not be valid. Rather, when x b tends to 0 as well as x a tends to 0, T del S mix is greater than del H mix for this situation. Of course, as we go towards the right here or towards left, this condition would start prevailing. So, minus my del G mix, which is this expression, would look like this. So, there will be dip around a pure range side on both the sides when x b is very low or when x a is very low, whatever could be the situation, since this value is always finite and this value is becoming minus infinity on pure metal sides. Now, if we have a situation like this, my del G mix is this one, this is del H mix, this is minus T del S mix. Now, if I try to see what would happen to the G2 line, this was my this is G A 0, this is G B 0, this is G 1 equal to X A G A 0 plus X B G B 0. We have to just add this value with this value, and here also the situation would be same. Around these zones there will be dip in G2 line, and then there will be again upward movement of G2 line. So, my G2 line would be like this. So, this would be my G2. Now, final solution free energy line would have a situation like this. So, now if let us say this is the effect at any temperature T, but if let us say the temperature goes up, increases, and if it increases, then the change would be not here, rather it will be change would be here. So, this line would start going down, because as the temperature goes up, this thing would go like this. So, at some point of time, let us say this is at temperature T3, at T3 del H mix would be less than minus T del S mix at all concentrations, all concentration. So, that time this G2 line would also keep on changing, because if it is T3, then my del G mix would be gradually would go down, because ΔGmix is nothing but this is ΔGmix when T equal to T3. So, everything would go down, this entire line would go down and it would come to this place. So, that time my new G2 line would be simply this. This would be my G2 T equal to T3. So, these two conditions can be possible. That means, at low temperature we have a situation this, at high temperature we have a situation like this, in those cases where ΔHmix is positive. Now, if I try to deal with only the G2 line, let us say I have drawn this is 0 point G value. So, if the situation is like this is G2 of some solution, some phase, then I could see that the common tangent can be drawn and that common tangent passes through these 2 points. And if these 2 points are passing through that common tangent, that means these two compositions will be in equilibrium. And interestingly, if we see this is my XB, at this point it is more of A rich region and this is B rich region. Now, there is a possibility that these two phases would appear. Interestingly, initially we have considered that both the A and B pure metals have same crystal structure and the solution, resultant solution is also having the same crystal structure. That time we are getting this G2 line to be continuous from 0 to 100% B, and we are having two solids, one with a composition X A of solid 1 and then this is X or XB, I can put it in terms of XB, this is XB solid 2, solid 1 and solid 2 they are in equilibrium. And actually two different solids are forming with the same crystal structure, but having two different compositions. And these compositions, for example, if we try with a composition this which is X0 initial composition, these initial composition will be distributed into these two solids of different compositions, and when these two solids are forming we are getting an equilibrium and one solid is having richer in A, the other solid is having richer in B. So, this is called phase separation. And because of this particular situation, we get to see eutectic as well as eutectoid phase diagram. Let us consider eutectic. Here also the two sides, two pure metal sides are having same crystal structure, the resultant is also giving resultant solution is also giving the same crystal structure. So, if we have a situation, free energy composition situation like this, let us say this is 0, and if the temperature is less than Tm B and less than Tm A, so I would get this is liquid, and then this is G A 0 of solid, this is G B 0 of solid, and this one we are taking it as a reference. So, that means 0 value. And now we could see that, and this shape is coming due to this particular shape is coming because in solid condition del Hmix is greater than 0, and this is G2 of solid, and this is G2 of liquid. Now, we could see that there could be a common tangent which will connect this point and this point. So, I can mention the equilibrium condition mu A, and this would be then solid 1, this would be solid 2, solid 1 equal to mu A liquid equal to mu A solid 2, and similarly here I can write B solid 1 equal to mu B liquid equal to mu B solid 2. So, if I try to see the plot on T xp, T versus xp, so if this is my temperature T, where I could just drop down these points and I could get these 3 points on this equilibrium points on this temperature, and where liquid and 2 different solids structure are same, but they have different composition. One is A rich, another one is B rich. So, they are in equilibrium. Now, if I try to see a temperature which is greater than, let us say this temperature is TE, then situation could be like this. So, here I have a common tangent and there is one more common tangent. So, this is solid 1, this is solid 2, this is G2 solid and this is G2 liquid. So, this is XB solid 1, this is XB liquid with in equilibrium with solid 1, and this composition would be XB liquid in equilibrium with solid 2, and this is XB solid 2. Now, this at this temperature, if I try to see this temperature which is greater than T, then I can have those points. So, let us say this is my point, these are those points, those are those equilibrium points. This is this composition and this point is this composition, this corresponds to this composition and this corresponds to these compositions. And if we have a situation like this is at T, if the situation is like this is G2 liquid, this is G2 solid. So, the only I could get a common tangent like this, which is this one would be solid 1, this one would be solid 2 with a composition X B solid 1. Now, this is in equilibrium with solid 2 and here it is X B solid 2 in equilibrium with solid 1. And that time we can also see this, we can plot these 2 points, and if the temperature, this is let us say T1, T1 is less than TE, that time we are getting this situation where liquid line moves up. That is where the liquid line is always above this particular common tangent, this common tangent between S1 and S2. That is why the liquid cannot be formed, liquid would become metastable, the stable phases would be S1 and S2. So, we are getting 2 different regions. This point is correspond to this and this point corresponds to this composition. So, now if I try to continue these points as with the temperature, I would get those locuses like this, and on this side this locuses would be like this, and here also I get these points, and here also these points, and so if I combine those I would get a phase diagram So, this is my liquid, this is solid 1, this is solid 2, this is S1 plus S2, this is solid 1 plus liquid, this is solid 2 plus liquid. So, these are the equilibrium phases, and this diagram is nothing but eutectic phase diagram, and where this is eutectic temperature. And it indicates that because of this particular nature of this particular G2S, which is because of ΔHmix in the solid state is greater than 0, we are getting an eutectic phase diagram. Let us stop here. We will continue our discussion in our next lecture. Thank you.